place. So too much actually to generate it to support this place. The task was first to lay out the vanadium battery and storage. So we decided to have a 21 kilowatt, 120 kilowatt hour flow battery and 60 kilowatt, 60 kilowatt hour, 30 kilowatt lithium-ion battery. It's a phenomenal. And then, of course, we also wanted to lay out the heat demand. So with this, we use the PV generation and try to see when we have excess loads, and of course then lay out the hot water.
L'audio, come lo verifichi?
And so we calculated that we need a heater power of 75 kilowatt and would have a savings of 32.5%. So this is the scheme of the system. So you can see that we have the lithium-ion battery, we have the battery, we have a thermal coupling module where we could put into the storage or put it out. We have a cold water storage, and we have a heating device, a heating stick. Yeah, to heat it up in the thermal couple module. We also have electric chargers in the grid. So we have the student dormitory, which has, of course, a load, and we have a grid connection, of course. Yeah? And we have a connection to the community heating. This is also as a backup, of course. Yeah? And the KIT made an EMS with a real-time control of 250 milliseconds, centralized and capable of real-time optimization. So, okay. And they used for this Open EMS by Fenecon to design the EMS. So a lot what they do is to optimize the use of the hybrid storage, especially when to charge and when to charge the flow battery and when to charge the lithium-ion battery. And they looked at some strategies to, especially at different weather conditions, whether you have clear sky or you have heavy moving cloud or rainy day, they try to optimize the system. So especially the charging and discharging strategy to get the maximum efficiencies. So you can see always the first two columns are with a redox flow battery and the lithium-ion battery without a strategy, and with a strategy, the savings or the gains in charging efficiency. And the idea, what they also looked at is that they have less idle time, especially for the lithium-ion battery, because at high state of charge you have more aging of the system. So the strategy which they most drive, for example, here is a sunny day. We can see the green is the solar curve, what you get. You can see the red is the load, the red curve, the dark red curve. And you can see in the dotted lines are the state of charge. You can see on the right side the scale of the flow battery as well as the lithium-ion battery. And you can see that directly when the solar irradiation starts and you have excess energy, then they started to first charge the flow battery, and later during the end of the day, they started to charge the lithium-ion battery. And also they start to discharge the flow battery first, and then at the later days, at slower discharge rates, they discharge the lithium-ion battery. And with this kind of strategy, they got some efficiency gains. Yeah, especially here. Correct. Also, of course, in the coupling module, the idea was also, of course, to increase efficiency of the flow battery. You have usually, a lot of people say 75% efficiency, but the flow battery actually has 50 to 60% efficiency. Usually at that operation point, you operate the system. This has to do mostly with pumping losses. Your pumps are seldom in the optimum, or also with other losses. And mostly of the losses are heat. there are some other losses which are due to osmotic losses in the battery, but mostly is actually heat. And so one idea was to gain more efficiency in the system with applying also the waste heat. And it could be shown in the couple module that 14% of the waste heat could be utilized by the battery itself. So with this coupling module, the big surplus of energy from this, especially the solar plant, could be utilized to heating. So they got a self-sufficiency rate of 75% and a thermal self-sufficiency of 14%. So now I come to our contribution. So usually vanadium battery electrolytes are not really good at to be used as a heat storage, because usually you have an upper temperature limit of around 38 degrees. For heat storage, it needs to go up to 50 degrees to be used efficiently. So what we did is we modified the electrolyte. So what kind of electrolytes do we have? So usually it's differentiated between high energy density electrolyte, which is usually unusable in an application because the temperature window is so narrow. There are some mixed acid electrolytes, which we don't favor because they can develop chlorine gas at higher state of charge. So in most batteries, actually, you have the low concentrated regular vanadium electrolyte, which consists of 1.5 to 1.8 mole per liter vanadium dissolved in sulfuric acid and with some additives like phosphoric acid. This is a typical electrolyte you have. But it has some flaws. When you increase the temperature, then you will notice that the chemistry will change, and it's a very slow process, but it happens that you will have precipitation. And this 40-degree or 38-degree upper limit is only for the charged electrolyte, but is inevitable. So usually you cannot use vanadium electrolyte as a heat storage. No? You can try to use additives, some phosphates, you will get a higher induction period. So instead of that it takes place in 2 days, it can take up 6 days, but you cannot avoid it. So in our study, what we did for BFlow project, we looked at a different strategy. So as I said, usually want to increase energy density. For this project, we said, well, let's go the other way, maybe dilute the electrolyte so that it gets more stable for higher temperatures. And especially we know that acid content has a big influence on stability. We said, let's dilute it, put more acid inside, then we can maybe gain some stability. So dilution was here the issue, what we wanted to achieve. And of course, we wanted to have a compromise that we have enough energy available to run the battery operation, but still be able to support higher temperature levels. So first of all, we defined key parameters for the composition. So the problem what you have is we know that if you have free acid, so hydronium ions, as a chemist would say, in the electrolyte, you would have a higher stability. But the problem is you cannot measure the acid content. You cannot measure the pH. You cannot put a pH electrode in such an electrolyte. It's much too concentrated. And you would get a wrong reading if you use a pH meter. So the acid content, free acid content, is an unknown. But what we can analyze is the total vanadium, as well as in which states the vanadium are. We can analyze the total sulfate content. This is also something what we can do. So one of our parameter was a ratio between the vanadium and the sulfate. And the other thing what we could measure is the conductivity. And these two parameters we used to define electrolytes. And So we made several compositions where we diluted electrolyte in a certain way or concentrated. So we use a concentrated electrolyte and diluted it with sulfuric acid and water to gain several concentration where we have different total vanadium and different total sulfate concentrations. And also measured the conductivity. You can see the conductivity as a color scale. So of course, when we have high sulfate concentrations, we get higher conductivities. But of course, it's also disturbed by the vanadium concentration. So higher vanadium concentration usually means less conductivity. And so we made this ratio. This is always the number you can see below the dot. This is a ratio between the vanadium to sulfate content. And then we looked, we have black dots, which are with 0.05 molar of phosphoric acid as a stabilizer and 0.1 molar of stabilizer. And we looked, made stability testing with all these compositions. And we looked at two stabilities which are important for electrolytes. One is the higher temperature of the charged positive electrolyte for the positive pole, and also for the negative pole at -20 degrees, which is also important, the low temperature stability, especially for the negative pole electrolyte. And there we you could see the color coding gives you the stability regions. So when it's red, it's especially stable. When it's blue, it's getting more and more unstable. And so we identified that, for example, if we dilute it to around 1.4 mole per liter, we don't lose too much of the originally 1.6, but we would gain, if we increase sulfate concentration, we would gain much more in stability in our electrolytes. The problem what we also have is this is only one aspect of electrolytes. So the temperatures is one aspect, but all the others has to work. Especially what we notice is, especially when you go to higher temperatures, the stability of the negative pole electrolyte is also in risk. So this means usually the negative electrolyte is somehow stabilized, kinetically hindered. It would decompose to vanadium-3 and hydrogen thermodynamically, but this is hindered. But if you increase the temperature, this reaction can get more favorable. And so also we did a lot of headspace, gas chromatography, headspace, online mass spectroscopy to determine how much gassing you have at higher and elevated temperatures. Because if you, for example, put too much, this has a tremendous effect. If you operate the battery, for example, at longer range for 50 degrees, you don't want that this unwanted side reaction spoil your electrolyte and lead to a lot of shift in the electrolyte. So we did a lot of testing. Fortunately, the 1.4 electrolyte, which is electrolyte A, so we have a program where you have 1 hour peak where you heat it up and then cool it down, and then have a 19-hour heating period, and in between we measured, and we could actually show that the 1.4 molar electrolyte has less gassing than if we operate, for example, 1.7 molar electrolyte. This was getting us quite thrilled that this was also stable. So we then make a comparison between a 1.7 molar, which is a more or less a regular electrolyte, to this diluted electrolyte. And what we also could see is that we have much higher power densities, and this has to do with the higher conductivity. So in general, you could say, even though you're diluting the electrolyte from 1.7 to 1.4 molar, you gain thermal stability, you use less vanadium, but you have a better capacity utilization. Actually, we don't lose energy, actually. So this was really surprising for us. So our diluted electrolyte has the same capacity, practical capacity, than the regular electrolyte. And so we actually made an electrolyte which is cheaper, more temperature stable, and cost less. So this was quite interesting to see. So always when we look in this space, you have borders and limitations. Either if you go too high in acid, you can have side reactions like gassing. If you go too low in acid, you have lower temperature stability. So you have a lot of limitations which you have to take care when you design such electrolytes. So we have to test it all now. And this is actually the end of my talk. So we finally made an electrolyte which actually is as good as a regular electrolyte, but has higher thermal capacity and that we can use in our B-Flow project. So I'm open for any questions.